Tells us that the dx dt is -8 meters per second, and it tells us that x equals -4 at our instance, and we're looking for d theta dt. Let's draw a picture. Okay. Instead of the square root of negative x, what if the negative was gone? What does the square root of x look like? It's like a sideways parabola for the top half. That's what the square root of x is. So if I plug in a negative in front, what does that do for our transformation rules? It tells us to reflect it about the what axis?
X.
The y-axis. The y-axis. So this graph looks like that. At some point, at -4, our particle is up here, and we are looking for that theta. So as the particle moves, this theta, all right, gets smaller, right? It looks like it's going to get smaller and smaller and smaller. Okay, so where do we start? We're looking for d theta dt. We have dx dt. We don't have dy dt. Can we find dy dt? Yeah, by just taking the equation. So the derivative of our equation is dy dt equals -1/2 times the square root of x times dx dt. I think that's right. Where does the negative come from? Oh, square root of negative x. Where does the negative come from? Chain rule. And then when x is equal to -4, we get -1/2 times the square root of -4, and dx dt is -8. So the square root of 4 is 2, so -1/4 times -8. 2. We'll say meters per second. That's dy dt. Okay, so there's dy dt. But we were looking for theta. So how can we find, so we need an equation involving theta. What kind of equations involve angles? Okay, we have triangles. Trigonometry perhaps. Okay, so we're looking for theta. We know things about x and y. Which trig function will involve x and y? The tangent of theta. In fact, doesn't the tangent of theta equal y over x? Yes, I hope. So now we can take the derivative. All right, with respect to time, the derivative of tangent is what? Secant squared theta times d theta dt. The derivative of y over x, which rule do we have to use? Quotient rule. So the derivative of y is what? dy dt times x minus y times the derivative of x all over x squared. All right, let's start plugging things in. Let's start on the right side. dy dt was 2. X is -4. Y. What is y? 2. How do you get that?
Original equation.
Yeah, I plug in. I know x is -4, so I plug -4 into the square root of -x, and you get the square root of 4. Square root of 4 is 2. All right, there's those two. And dx dt was what? -8? All over -4 squared. We're looking for d theta dt. And now we're trying to figure out secant squared theta. So the secant of theta. Instead of solving for theta, trying to figure out the angle, let's use our triangle. I know that the x distance of this triangle is 4. We can even say -4. The height of this triangle is what? 2. So by Pythagorean's theorem, the hypotenuse at this particular moment in time, because we're taking the derivative, so it's like taking a snapshot, because the particle is actually moving, but at this moment in time, what's the hypotenuse?
2√5.
The square root of 20. Some people said 2√5. That works also. Right? Because 16 plus 4 is 20. And then it's the square root of that. Okay, that's Pythagorean theorem. Which means that the cosine of theta is negative 4 over the square root of 20. And then the secant of theta is the reciprocal of that. Right? So secant of theta is the square root of 20 over negative 4. So we write square root of 20 over negative 4. We never even had to figure out what the angle was. We just used our triangle and solved. We didn't solve for theta, we solved for the secant theta. It's a lot easier to do that. I just want to emphasize that because we had a problem like that a couple months ago and I didn't emphasize as much as I should have. Okay, so solving, this becomes 20 over 16 times d theta dt equals negative 8 plus 16 over 16. D theta dt equals 8 over 16 times 16 over 20. 16's cancel. 4 goes into this 2 times, that 5 times. We get 2/5 radians per second. How do I know we're in radian mode? Anybody? Ryan, how do we know if we're in radian mode?
I was just going to say we're doing calculus.
Okay, right. Well, I've told everybody in this class we're always in radian mode. If we were not in radian mode, do you remember? Anyone remember what happens? What would have happened? That would have broken down.
When you take the derivative of tangent.
Right. When you took the derivative of tangent theta, if you're in degree mode, you have to use a chain rule, and it gets kind of weird. All right. The fact that the derivative of tangent is secant squared, that's only true in radian mode. All right. So just throwing that out there. Any questions about how I approached any of this? Yes. And we did need dy dt. We had to use dy dt when I figured out, y over x. I suppose you could have substituted square root of negative x in for y, use the chain rule there, and only use your dx dt. That would have been fine too. You would have gotten the same answer. All right, sounds good, Max.